Well, hello everyone. Today's lesson is essentially to cover the work that would be covered on Wednesday, the 9th of November. And the section that we're going to do today is section 11.5, the alternating series test. Like all the other tests that we've covered so far, the alternating series works with a special subgroup of all series. And they are called alternating series. So let me show you what an alternating series might look like. Here's an example of one. Now, the key features is that you start with a positive number, then you subtract the next, then you add the next, then you subtract the next. So it's plus minus forever. Now, in this particular case, it started with a positive, but it's okay. You may start with a negative number, and then you might add a half, and then we take away an eighth, and then you add 132, and you add and subtract forever. These are examples of alternating series. Now, if you are looking for what does an alternating series look like in general, they tend to look like one of these two situations. There is going to be an expression. This expression here will probably be a fraction like 1 over n squared, n plus 1 over n cubed minus 1, that kind of look. And this piece here, the negative 1 to the n, essentially what that does is it generates, in this case, this sequence. If you plug in n equals 1, the answer is negative. When you plug n equals 2 in, well, negative 1 squared is positive. N equals 3, it's negative. So this particular one would generate the negative plus pattern you see here. The other version looks very similar with one minor change. Now, in this one, if you plug in n equals 1, you get negative 1 squared, which is positive. Then n equals 2 gets you negative, then n equals 3, and so on and so forth. So an alternating series essentially is a series where the terms alternate between plus and minus for eternity. And the alternating series test is a way to tell whether a particular alternating series converges or diverges. And here is how that test is kind of stated. So if we have an alternating series, let's take this one. First thing is, you have to prove that the series is decreasing. And secondly, if the limit as n tends to infinity of just this piece is equal to 0, then the series converges. If, however, the series is increasing, in other words, each term is going to be bigger than the term before, or if the limit as n tends to infinity is not 0, right? So some other number, could be 4, could be 24, but it's not 0. If this happens, right, the series increasing, or if the limit as n tends to infinity is not 0, then in that situation, the alternating series will diverge. So there's our test. If you want to prove that it's a convergent one, prove that it's decreasing, right? These terms here are getting smaller and smaller, and prove that the limit as n tends to infinity of the individual terms is 0. If you want to prove that it's divergent, prove that this is increasing, or show me that the limit as n tends to infinity of this is not 0. So let's dive right in and look at an example of how that might work. This is a version of question 3. So we have -1 to the n minus 1 over 7 plus 6. That's my version. Now the guy that we are calling AN is the bit that doesn't include this. So it's always going to be positive because of that, right? It's this guy here. Now I need to prove that that is decreasing or increasing, I guess, and depending on what happens here, I can then move on to the second part of the test. So the easiest way to prove something is decreasing is just like in the integral test, and that is to prove that its derivative is negative. Right, so I'm going to take this and call it f of n, and I'm going to write it in that format because I think it's a little bit easier to differentiate when you write it like that. And the derivative is, essentially, this is going to be a power rule, chain rule combination. You multiply by the power, you reduce the power by 1, and then you finish with the derivative of the inside function, which in this case is just 2. And so the derivative is -2 over 7 plus 2n squared. Now we know that n represents whole numbers, 1, 2, 3, 4, 5, and so on. So if I look at this expression, well, the top thing is -2. That's always going to be negative. And the bottom, well, whatever that happens to be, if you square it, it's always going to be positive. So this combination means that the derivative is negative. So that means, right, since the derivative is negative, the function is decreasing. Well, that's good news. We kind of got over the first article. Now what we do is move on to the second phase, and that is we find out what does the limit, that's kind of phase 1, what is the limit, right, of this guy going to be as n tends to infinity. So we're only interested in this piece, not the -1 part. So the limit as n tends to infinity of 1 over 7 plus 2n. Now don't make a meal at this. This one can be done very simply by just brute force. 2 lots of infinity are infinity, 1 over infinity, and the answer is 0. So our conclusion is that this alternating series converges by the alternating series test. And that's it. So take the individual terms, differentiate them if you need to, probably you will. Prove that it's decreasing. Done. Then find the limit as n tends to infinity of this guy. If it is equal to 0, which it is here, it converges. If that was equal to 2, the conclusion would be that it diverges. If that was infinity, it would diverge. If that was a half, it would still diverge. It must be 0 and only 0 if you want to get convergence. Try something a little bit uglier, I guess. Yeah, uglier, I guess is a good description. This is a version of question 4. And I'm going to cut some corners here, only for time purposes. So we have -1 to the n. We have an n to the 4 over an n to the 4 plus n squared plus 1. And let's just assume that I've already proved that it's decreasing. And I would do that by taking this guy here, differentiating it, tidying up as best I could, and prove that the derivative is negative. So I'm now just going to do the second part of the puzzle, which is I'm going to prove or find out what this is equal to. And then based on what it's equal to, that I'll either be able to prove that it converges or it diverges. So we have an n to the 4 over n to the 4 plus n squared plus 1. So we're trying to find the limit as n tends to infinity of this guy. Now you could do L'Hopital on it, but I think it would be less work if you divide the top and bottom by n to the 4. So it now becomes the limit as n tends to infinity of 1 over 1 plus 1 over n squared plus 1 over n to the 4. And at this point, I'll do brute force. So it's 1 over 1 plus 1 over infinity, I guess squared, 1 over infinity to the 4. Well, that's 0 and so is that. And so the limit is 1. So we've just found that the limit as n tends to infinity of the individual terms, an, is 1. And the conclusion is, well, since that is a number, right, but the number isn't 0, the series, this guy here, diverges. If the limit is not 0, it diverges. If this limit was 0, it would converge. And that's by using the alternating series test. Try the next one. Well, I'm only going to set up 5. I won't really do a lot in 5. We're being asked to find out whether this alternating series converges or diverges. I think it is, in some respects, at least when you want to find the limit, it's a good idea to rewrite it like that, because you can prove that this is decreasing and it's not too difficult. And can you take my word for it that its derivative is negative? And if you want to do this, it's a lot easier to find the limit of that as n tends to infinity, and that would be your answer based on whatever you get. So let's try this one. This is a version of 6. Again, it's an alternating series. Well, all of them are. Again, I'm going to, for time purposes, I'm going to pretend that we found its derivative and we showed that it was negative, right? So it is definitely decreasing. That's something you're going to do. You'd use the quotient rule, call that n to the half, and do what you need to do. So let's just focus on the second phase, which is finding the limit as n tends to infinity of this guy. Now, normally I would say if you see a square root, avoid it. Like the plague, if you're going to do L'Hopital show on it, because the square roots don't typically, almost always anyway, behave well. You just end up with an ugly answer. But this is an exception. This one is not that bad. If you call this guy n to the half, its derivative is 1/2 n to the -1/2. And if you differentiate the bottom, you get 2. Which means that this is now going to be the limit as n tends to infinity of 1/4 n to the half. And I'm going to just make that look a little bit prettier. 1/4 square root of n's. and then just do brute force. The square root of infinity is infinity, 4 infinities is still infinity, 1 over infinity, 0. It decreases, its limit is 0. Conclusion, the series converges by the alternating series test. Now let's take an example of a square root that using L'Hopital probably wouldn't be a good idea. In fact, I know it would probably be a very bad idea. So let's look at question 8 and show you how you would tackle it if you weren't able to use L'Hopital or you knew it was a bad idea to use it. It's got a square root in it. It's just got a much uglier square root in it, and that's what makes the difference, that extra plus 4. Now I'm going to assume that its derivative is negative, and so that it's already decreasing. So you're going to differentiate this function, and you'd use a quotient rule on it, and you'd have to call that guy n cubed plus 4 to the power of half, but eventually you'll be able to prove it's decreasing, at least for n greater than or equal to 1, which is the only values that you're concerned with. So let's focus now on the limit as n tends to infinity of this guy. If I tried L'Hopital on the bottom, it would be, God, it would be ugly. In fact, it would be worse looking than this guy. And you kind of know when that happens that you shouldn't do it. So I have a backup plan. I'm going to divide the top and bottom by, well, I have a choice. I can divide the top and bottom by n, or I could divide the top and bottom by the square root of n cubed, which I think is a bit ugly. So I'm going to choose n. Only I'm not going to call the bottom one n. I'm going to call it that version of n, the square root of n squared. And the reason I need to do that is that if you're going to divide or multiply something, you really do need them to look the same before you start multiplying or dividing anything. So this now becomes the limit as n tends to infinity of 1 over the square root of, that guy gets you n, and that guy gets you 4 over n squared. And now I can do brute force. It's 1 over the square root of infinity plus 4 over infinity squared. Well, 4 over infinity squared is 0. Infinity plus 0 is still infinity. The square root of infinity is still infinity. That guy is 0. Yep, we got yet another conversion. So the series, that guy there, converges by the alternating series test, because that's the one we used to do it. Now I'm going to switch over in a few seconds and show you some more of the homework questions. We'll just talk about the kind of the details that you need to find its limit in particular. So here we go. If you were going to do question 8, you see this one here? That guy there? L'Hopital might work. I'm pretty sure it doesn't. What you should do here is divide the top and bottom by the square root of n. In this question here, you want to take this guy here do L'Hopital on them. It works well. In this one here, do L'Hopital. It works well. In this question here, this cosine of n pi is a bit of a trick question. The cosine of n pi is actually the same thing as -1 to the power of n. I'll tell you why that. If you plug in 1, you get the cosine of pi, which is -1. If you plug in 2, you get cosine of 2 pi, which is +1. You put in 3, you get cosine of 3 pi, which is -1. So essentially, it just does -1 + 1, -1 + 1. So think of that guy as really just -1 to the n. Now, if you do it that way, can you see that this question is very simple to prove that it's decreasing? And it's very simple to find what the limit is, because you can just do a brute force on it. It comes out really nicely. This one here, you'd be pushed, but we're not interested in question 13 onwards in proving that it converges. They're already telling you that it does. And our job is to find the answer or to find the value of the series correct to 4 decimal places. So I'm going to be showing you that later. But before I do that, let's jump way back to the beginning and look at some questions that we haven't tackled yet. Question 1 is an alternating series. It goes 3/4, take away 3/6, plus 3/8, take away 3/10, plus or minus forever. And we are going to be essentially finding out, does this alternating series converge or not? What makes this one different is we don't have a formula yet. We need to figure out how to make this alternating series work. So it's going to go sigma n = 1 to infinity. Now, this series starts with a positive, then it goes negative, starts with a positive, then it goes negative. So the pattern that we're looking for is plus minuses. Now, there's only 2 versions that you need to concern yourself. There's the one that looks like that, and the other one looks like that. Now, if you plug -1 for n, if you plug 1 in here, you get -1 as your answer. So use this series if it starts with a negative and then does a plus. If you plug 1 to this power here, n = 1, you get 1 + 1 is 2, and -1 is squared. So use that fella if the series starts with a plus, and use this guy if the series starts with a -1. Well, we start with the plus, so that's why I'm using that. Now it gets a little bit messier. We need a formula for an. And there's no one way to do this. It's really just a case of looking and seeing patterns. If you look at the first term, it's 3/4. The second term, it's that guy. The third term, it's that guy. The fourth term, it's that guy. You're kind of trying to find out what would it be, right, for the nth guy. What would be here? Right? So I look for patterns. The first one's an obvious one. Everything on the top is 3. You don't need to worry about the plus minuses. They've been taken care of. What you do need to do is figure out a pattern, a formula, for when you plug in 1, you get 4, and when you plug in 2, you get 6, and you plug in 3, you get 8, and you plug in 4, you get 10. Now, what I noticed, and hopefully you did as well, that essentially what you're doing here is adding to each time. And we call that an arithmetic, right, sequence. And for an arithmetic sequence, if you add 2 all the time, you're going to get a 2n. And then you'd normally have to add or subtract something to get it to work. The only time 2n would be correct would be if it was 2, 4, 6, 8, 10. So you can see that if I plug in, I know at random, 3. 2 lots of 3 would be 6 according to this formula, but I need 8. So I need an extra 2. So what we now have is everything that we need. And that's the guy you're going to prove is decreasing. And then you're going to do the limit as n tends to infinity. And it comes out really nice and really easy. Here's the next one. Okay, let's see if we can generate what the series looks like. It's going to n equals 1 to infinity. Right. Well, it starts with a positive. If you start with a positive, you use this guy. So that takes care of the signs. Don't you worry about them. Now, the first answer gets you this. The second answer gets you this. Third answer gets you this. Fourth answer gets you this guy. You're trying to find the nth answer. Well, everybody is a fraction and everybody in the top's 1. I know everybody is a log. The first answer is 3, the second answer is 4, the third answer is 5. As you notice, if you just add to the thing, you get the guy. Here is the formula that you need. And now you can do the alternating series test and everything is, hunky-dory, and you should be able to do it. And that pretty much brings us to the next phase of these questions. And in these questions, the ones that we're going to do now, that's the last few questions in the homework, I think it starts at 13 and goes all the way to the end, is that you already know that you have an alternating series, right? You're told it. And your job is to approximate what it would add up to 2 or 3 or say 4 decimal places, right? To a certain degree of accuracy. So you go n equals 1 to infinity. And this is a version, this is question 13. And it happens to be -1 to the n over 3 to the n times n factorial. And I'm kind of glad I don't need to prove that that is decreasing. I think it'd be very hard to prove it, except just by inspection. It's pretty easy to prove that the limit is 0. So I knew it would converge even though I don't need to prove it. This is the property that we're going to use. If you use S of k, S of k is called a partial sum, and k is how many guys you use. So if I use only k terms, right? K could be 5. That would mean I'd only use the first 5 terms. Right? If I use that to approximate the answer, it wouldn't be the exact answer, right? Because it's only using the first 5, right? The first k terms. So there's a bit left that we haven't used. But what the alternating series test says, it's remarkable, but it's true. It says that the error, right? What's the worst case scenario? The error is plus or minus the next term. So if I use, for instance, if I used S5, right, to get my estimate, that would be basically just adding up the first 5 terms. The error, right, would be plus or minus the 6th term. And the 6th term here would be -1 to the 6, 3 to the power of 6 times 6 factorial. So in question 13, you're told that this converges, and we are being asked to estimate the answer, estimate what this adds up to 4 decimal places. So the way I'm going to do that is I'm going to go and find e to the k, which is this guy. In fact, I don't need the -1 guy, I can just do 1. Right, that's e to the k guy. And I want him to be, Well, to 4 decimal places, you need 0.00005. Because if you round something off to 4 decimal places, it's the 5th decimal place that decides do you round up or down. Now, this guy here is probably nicer to write down using scientific notation. So that's the error that I'm trying to find. So I need to solve a weird equation. For what value of k is this guy equal to that very small number? Now, before you get too worried and think, oh God, that's going to be the worst looking equation in the world, how on earth am I going to solve it algebraically? Let me tell you, that's probably not the way you should do it. What we're going to do instead is do a clever little trick. It's called guess and check. And let's show you how that works. I hope you're looking at a calculator right now. Okay, I have 1 over 3 to the k factorial. I am just going to guess. My first guess is that k equals 5. Right? In other words, I need 5 terms to get the accuracy that I want. Right? I want, or at least the 5th term is the accuracy I want. So I'm going to go 1 divided by, almost forgot that. Put a bracket around it for safety. And then do 3 to the power of k. So that's 3 to the power of 5 multiplied by k factorial. So that becomes 5 factorial. So hit the math button and move over to, I think it's probability and choice 4, right? And I forgot to put in the 5 first. 5. Then I do the factorial. Number 4. And then you finish your little bracket. And the answer we get, oh, I got really lucky here. The answer is 3.4 times 10 to the negative 5. That's what that e minus 5 means, which is pretty much exactly what you need. That's on the level that we wanted. So let me nip over here and just show you what we got. Now, I wish I had planned this because I wanted actually to be wrong so we could do the guess and check. But this guy is pretty much the same as that. In fact, it's a little bit smaller, right? But that's okay. That tells me that I only need to use the first 4 or 5 terms, depends on, if you want to say that needs to be a little bit better. And that would then be, let's suppose it's S4. All you need to do then is do n equals 1 to 4, negative 1 to the 4, negative 1 to the n, 3 to the n factorial. And if you calculate that for the first 4 terms, the answer that you get will be the answer to this fella to 4 decimal places of accuracy. So it does involve a lot of messy stuff, but here goes. Negative 1 to the n, 3 to the 1 times 1 factorial. Right. And actually, negative 1 to the n is negative 1. Right. So then it's plus 1, 3 squared times 2 factorial. Then it's negative 1, 3 cubed times 3 factorial. And then it's plus 1, 3 to the 4 times 4 factorial. And when you add that horrible mess up, it will be the estimate for what this series adds up to, correct to 4 decimal places. Now, can we pretend for a minute that I didn't guess right on the nose on my first guess? Let's suppose I guessed k equals 7, right? Just for argument's sake. Now, I'm just going to go in and do it in the calculator. So you just have to trust me. I'm putting these numbers in the right place. So I'm going to do 1 over 3 to the 7 times 7 factorial. So this would be 1 over 3 to the 7 times 7 factorial. And the answer I got here was roughly 9 times 10 to the minus 8, right? That's too small, right? That's more than we need. And then can you pretend that after I did that one, I may have chosen k equals 4, just for argument's sake. And if I had chosen k equals 4, the calculation would have been 1 over 3 to the 4 times 4 factorial. And that answer would have been 5.1. Well, I don't even need the 0.1, right? It's 5.1 anyway, times 10 to the negative 4. And that's 10 times too big. Well, I know that's too small and I know that's too big. Can you see that my next guess would have been 5 or 6, and then I would have nailed it. So it's not that I'm solving this algebraically. I'm basically guessing, and then based on my guess, if it was too big or too small, that would influence what my next choice for k would be. And eventually, it doesn't take too long, because you're not going to get a question where you need 312 terms to get the accuracy that you're looking for, right? And these questions they converge to whatever they're going to converge to very, very quickly with the first 4 or 5 terms. So kind of focus on those kind of numbers when you're doing the guess and check part. So for the last version of that, and actually the last question for 14, we are being asked to find an estimate for this particular alternating series, and they want, again, 4 decimal places. So I'm going to do -1 to the k. There, I did that again. You don't need that guy. I just need the rest. So k over 10 to the k to be equal to 0 0.1, 2, 3, 4, 5. So I'm looking for k over 10 to the k to be as close as we can get to that. So if k equals 5, I'll probably need 5 terms. If k equals 3, I'll need 3 terms, right? I've got my calculator, or will have my calculator set up here. And I'm going to do it on the calculator, so you won't see any writing here, because I think it's easier to see what I'm doing on the calculator side than, coming back and forward all the time. So here we go. Okay, my first guess is going to be 3. So it's going to be 3. I'll put it over here. 3 over 10 to the power of 3, which I happen to know is 0.003. Well, that's too small, right? So I'm going to pick 7. So it's going to be that guy. So 0.000007. Actually, I don't need to calculate. Those are pretty easy. So my next guess is going to be 5. 5 divided by 10 to the power of 5. Oops, I missed the power. To the power of 5. And guess what? That's nailed it, right? Bang on 5. So we tried 3, it was too small and too big, I should say, and 7, it's too big, and 5 is exactly right. It's a bit like Goldilocks, right? Too hot, too cold, and then perfect. So since this one's a relatively easy one to calculate, S5 should work. So S5 is from n equals 1 to 5, -1 to the n over 10 to the n. So it's plug in 1, you get -1 over 10, Then you add 2 over 10 squared. Then you take away 3 over 10 cubed. Then you add 4 over 10 to the 4. Then if you plug in 5 here and here, you take away that guy. Okay, let's see what that fella looks like. Now, I might have to change my answer a tiny bit. 5 is a good guess, but maybe you need 6 just to be sure, because something on the borderline like that might come out a little bit weird. So there's negative, oops, forgot the one. There's the first guy, negative 110. And then I'm going to add 2, well, essentially over 100, because it's easier to write it that way. That's 2 squared. Then I'm going to take away 3 over 1,000. Then I'm going to add 4 over what, 10,000? Have you noticed how small the terms are getting? Right, we've only done 4 terms and we're already at 4 10,000s. The next one is take away 5 divided by 10, 1, 2, 3. And that's my estimate. It seems to be negative 0.0831. Okay, so I'm going to go up to the top here, and I hope to see that answer. But if I don't, it just was, I needed one more to be sure kind of thing. So let's, hopefully we get the one I wanted. That looks to me like it's darn close to 0.831. I think the only difference would be that I needed to add one more term. So 0.827. Let's see if that makes any difference. Well, if I did the next term, it would be add 5 divided by, oh, guess what? It would be add 6 divided by 1. 1, 2, 3, 4, 5, 6. There we go. Now, I may have hit the button a little bit out, but I'm good. Why am I not getting it? Okay. Does it give me a solution so I can check it? I mean, I'm darn close. Here, click to you. Oh, they're saying you need 6 terms. But they added it up to 5, which is fine. And they say it's that when you do 5. Okay, then all that happened is maybe I forgot an extra 0 for 1, and maybe I put in 1,000 when I should have put in 10. So the answer does kind of match what we got. Negative 0.08265, and I got 0.831. So I think I just made a small mistake when I pressed the buttons on my calculator. And that, guys, is all that you essentially need to know from the alternating series test. So I will not see you until Monday now. Remember, your test will be available sometime in Friday, I suspect. I'll see if I can get it done on Thursday night, but I'm kind of busy. So it's more likely to be Friday as usual. And everything, including your test, has to be done by midnight Sunday. And I will be back on Monday. Those who want to, but I strongly suggest you turn up to the live version of this rather than kind of watch the video afterwards. So goodbye, and I'll see you soon.